everyone. I'm going to take some time and kind of go through the electric charge web quest that you had done the Friday before they kind of cut school off at actual school, Friday before e-learning, I guess. If you were not there that day or you left your packet at school or can't find it, I attached to this OneNote page a copy of the packet for you. So you can go through and kind of follow along, go through and kind of look back at the activities. I highly recommend that because this video will not be able to show you in order to go through the main points on this packet. I'm not going to be able to flip back and forth really between the activities themselves. So if I'm like talking a totally foreign language to you and you don't understand what I'm saying, I highly recommend going back to the previous OneNote page and really looking through some of these activities and trying to remake sense of this, especially since it's been a few weeks since we started looking at electric charges. So with that, I'm going to dive into this. I won't go through every single question on here. I'm going to go through probably the main points, and then we'll take it from there. So the pre-activity questions are asking you to just kind of identify what the charged parts of an atom are called. And it's been a long time since we talked about this, but inside the nucleus of an atom, you have different parts. You have positive charges, which are the protons, and then you have things that don't have a charge, and those are neutrons. Okay, so you have protons, and then neutrons are neutral. So those things do not have a charge. Around the nucleus of the atom, orbiting it, you have electrons. And electrons have a negative charge. So that's kind of where we're getting this information here. Protons are positive, electrons are negative. And these foundational atomic charges is what actually is responsible for the overall charge on different objects that we're going to see in this unit. So it comes from protons and electrons. It's kind of crazy. If you have a single proton or an object that is positively charged, it has an electric field around it. And the electric field around positive charges is kind of an outward force. I don't know why exactly it's outward. That's just what we observe. So you get this outward force on positive charges. If you were on your activity to move your positive charge around the page, it's still going to show the same pattern. Okay, it's always the same pattern. Arrows will always be represented away from the positive charges because that's what the force is showing us. The electric field around a proton always faces outward. Okay, that's just how we model this. It's away from the charge. Negative charges are a little bit different. They're actually the complete opposite because they're the opposite charge. Negative charges have an inward force. So if you were to look at negative charges and draw the force around it, for some reason, the negative charge always has kind of an inward force. And the way that I like to kind of think about this, I'm going to go back up to the positive charge here. One of my students one year said that you would want to spread positivity. So if you were positive, you wouldn't want to keep it all to yourself. So you would want to spread positivity. So that's kind of how they thought, okay, positive goes outward always. Whereas negative, if you have negative thoughts, you'll probably want to, not say them to your friends and make them down, that kind of thing. Same thing though with negative fields. If you were to move around your negative charge, you would always see the same inward field. So the electric field around an electron always faces inward, kind of towards the charge. So that's the basics of just positive charges and negative charges on their own. These next questions kind of look at the E-field sensors. Now the sensors that I think are in this activity are little orange dots, unless they change that on me. The little orange dots, if you kind of bring the dot closer to where your charge is, whether it's positive or negative, you notice that the arrow gets longer, and if it gets away, the arrow gets shorter as the sensor is moved away from the electron. And that is actually representative of the strength of the electric force field. So we would observe that the field is stronger towards the source of the charge versus away from the charge. So the electric field is stronger when it is closer to the charge. As distance is increased away from the charge, the field becomes weaker, and it would not necessarily exert a force on things that are much further away from it. I'd like you guys to take note that this is goal 2 in your study guide, goal 2A. 2A talks about the strength of electric fields. You'll want to know that distance impacts the strength of the field. Okay, distance impacts the strength. The closer objects are, the stronger it's going to feel that electric force. Okay. Moving on, we're going to look at how these different fields interact with one another. So in number 11 here, it says leave the electron on your screen, drop and drag a proton at least 4 arrows apart from the electron, and then draw the direction of arrows that you've created. Well, you are drawing how positive and negative fields are interacting with each other. And if you were to just focus on a positive field, you would once again observe that it always has that outward force. And then when it's put next to a negative field, they've actually attracted to each other, and they would want to move closer to each other if there's no friction or anything else or any other forces that are standing in the way, because opposites attract. So if you have this this outward force of the positive proton, it's going to be attracted to this inward force of the negative electron. So opposites attract. It's kind of like that old saying. Sadly, that's cheesy as it is, that is the truth when it comes to electric fields. So what force do we observe? Ooh, hold on. We observe attraction. And the drawing will be for 4A in your study guide. Knowing what attraction is and knowing that opposites attract, that is goal 1A in your study guide. So once again, take note of these study guide pieces on the side of your packet as we're going through this. Moving on to if you have like charges. When I mean like charges, I mean that you're dealing with 2 of the same charges. So if we look at this next example in number 13, we're looking at a positive charge interacting with another positive charge. If you have 2 positive charges next to each other, keep in mind that they each kind of show that outward force. And it's kind of visual, especially when we use protons, that some people get confused that these arrows show that they want to move towards each other. That's not actually what's happening. These arrows don't represent the movement, they represent the force. So you can see that the force is pushing on one another. These arrows are not representative of the way they move. They don't move closer together. They'd actually move further apart because they're repelling forces. If you have 2 of the same charges, they're going to want to repel each other. They're going to have a harder time coming in contact. If you have a positively charged object and a negatively charged object, there's going to be some resistance for them to come in contact because they have a force that's pushing against one another. That's what's going on here, and that's what you're observing. So make sure that if you have positive charges, you always have arrows showing that outward force. And in this example specifically, it's showing that they're pushing against each other. You have a force that's repelling each other, pushing against one another. Kind of think of it as like they're pushing on this wall in between them. They don't want to be by each other. And this goes with goal 1B and 4A. So 4A, once again, is the drawing. My pen got messed up. And 1B is kind of referencing that if they're the same charges, they're going to be repelling forces, and they're going to want to push each other away. So that's kind of the main gist of charges, positive and negative charges, how you would draw them, and their interactions with each other. I'm going to go to the second part of the lab here real quick. Number 15 says, what causes static electricity? It's the buildup of electric charges. So when I mean buildup, I mean that there are charges moving physically from one object to another. And I want to tell you that it's always electrons that move. And I'll show you an example of that when I talk about the second part of the activity. Before we get there, I just kind of want to go over some examples from everyday life where you experience static electricity. Number one, lightning is a very large form of static electricity. It's a giant spark in the sky. That's really all it is. Just a lot of charges that were built up in the sky and the clouds. And when they are built up so strongly, they'll want to discharge and get rid of some of those charges and try to become neutral. So that's what that electric shock is. That's just really big lightning. If you touch something and get shocked, so say you like rub your feet against carpet and go to touch a doorknob and you feel like a little shock, that shock is static electricity. You have built up charges from rubbing your feet on the carpet or something, and then you get shocked by it. Clothes sticking together in the dryer. If you have a dryer and you're taking clothes out and it's dry, even if you do this like in the dark, like I've done this at night where like I'm looking for something for the next day. If it's really dark in the room and you take clothes out of the dryer that like had kind of just ended, you can probably see some sparks, and that's another form of static electricity as well. I think what I'm going to do is stop there for this video, and I'm going to make another video about the second part of the lab. So that's that.